Here we are again with transformers, but this time with a small caveat. We are not extending them, we are trying to question them. Transformers have dominated almost every corner of machine learning since around 2017. NLP first, then vision transformers around 2020-2021, and now pretty much everything. As a community, we have started treating transformers almost like a holy grail. And to be fair, there is a good reason for that. Transformers are powerful because their parameters effectively adapt to the input tokens. Through self-attention, the model dynamically decides which tokens should interact and how strongly. That flexibility makes the architecture very attractive. But this raises a deeper question. Is this inductive bias unique to transformers? Is self-attention the only way to achieve this kind of dynamic token-dependent behavior? If we step back, before transformers, we already knew that multi-layer perceptrons or MLPs are universal function approximators. In theory, an MLP can model any function given enough capacity. So if that is true, then in principle, an MLP should also be able to do what a transformer does. So the real question becomes, what is missing? This is where gMLP or gated multi-layer perceptron comes in. At a high level, the architecture is really simple. You take an input embedding and pass it through a gMLP block. The input first goes through a channel-wise projection followed by a nonlinearity like a grail or gale. So far this looks like a standard MLP. But the real power hides in what is called Spatial Gating Unit. In transformers, the key idea is spatial communication. Tokens can talk to each other. Long-range dependencies can be modeled. A vanilla MLP cannot do this because it processes each token independently. The spatial gating unit fixes exactly that. Here's how it works. First, the input is normalized. Then, instead of projecting across channels, we project it across the spatial or token dimension using a simple linear projection. This spatial projection produces a signal that acts as a gate. That gate is then applied to the input using a Hadamard product, an element-wise multiplication. In other words, the model learns how much information from each spatial position should pass through. An important design choice is to split the input in half. One half is used to compute the gating signal and the other half is the part being gated. Empirically, this turns out to work better than getting the entire representation directly.